Now we have to start getting into our basic theory. Why does it move? Something's got to make it move, doesn't it? So I didn't warn you when you formed this circle, but you just volunteered. Sarah's going to be the battery. And what Sarah's going to do is give the Coulomb some reason to move. She's going to give the Coulomb of charge some energy. So her job is going to be, when she gets energy, the Coulomb from Millie here, what the battery's job is to do is to take the Coulomb and give it some energy. So let's see now. What Sarah is going to do, her job as a battery is to give the Coulombs energy. All right? Okay. So you got your job, Sarah. When you pick up a Coulomb from this hand,
do I need mine?
you have to, yes. You're going to lift the Coulomb up to here, right? About shoulder height. Okay? So you're going to grab it down there, and then when you pass it, you're going to lift it up here, give it some energy. All right?
Yeah.
Okay. Now, what were you doing before as wires? You were just passing Coulombs, right? You weren't giving the Coulomb any energy. You weren't taking energy away from it, from the Coulomb. You were just passing the Coulombs. So when you get the Coulomb, where are you going to receive it? Up high, aren't you? Sure. And where are you going to pass it off? Up high, about shoulder height. Same with you, and you, and you. So all of your Coulomb should be around shoulder height because they've got energy, right? About that high. Okay, thank you for volunteering to be the light bulb, all right? Oh, thank you, Doug. The light bulb is the key. You choose that person because they have to do something, right? And when these Coulombs that have energy get to the light bulb's going to use that energy to do something, right? And so I sometimes break light bulbs apart. The old incandescent light bulbs go around in circles. The new compact fluorescents, you know, they go around in a circle. Motors go around in a circle. So when you get this Coulomb of energy, I'll show you, hey, you're getting good. You're going to use that energy, and as the energy falls through you, you're going to turn around and pass it on at waist level because you've used up the energy, right?
Yep.
So you get the idea? You're going to take the Coulomb here, and then you're going to turn around, and you're going to pass it off there. Good for you. Low down. That's good. Okay. Now, we're going to get, you got, negative behavior. Right? Two Coulombs.
At some point.
What?
It had to come at some point.
Yeah, but as soon as you get a Coulomb, you have to pass it on, right? And anyways, you can never have two Coulombs in your hand at once. Okay. So you're going to have the block low down, right? And where's your block? Oh, got my language. Coulomb. You're going to have the Coulomb low down, right? Low down, right? Low down. Comes low down all the way back until we get to the battery. What's your job? To give the...
To give the Coulomb.
Sorry, you have longer strings there. The answers are in the back. It's really quite good. Battery's job gives the Coulombs energy. Okay? Oh, by the way, I might as well go for this right now. If you really want to make your grade 11 physics teacher happy, we can go a little bit of units. Now, we've already started units, by the way. And the first unit we've talked about is Coulomb. The blocks represent Coulombs. Now, when the battery gives the Coulomb energy, energy is a really valuable substance, right? So what are the units of energy because they're so valuable? Joules, right? So when the battery gives this Coulomb 1 joule of energy, and that's the energy it takes to go from here to here, we say that a joule of energy for every Coulomb, instead of saying joule of energy for every Coulomb, we got this fancy term for it. We call it a volt. Pretty simple, huh? Instead of saying a joule for Coulomb, we say volt. And so you start introducing the concept of what volts really means. Volts means energy the Coulomb has. All right? Okay, time to pass, because I can tell you're getting antsy again. Everybody knows their job, right? Where are your Coulombs? Up high. What are you going to do?
I'm going to spin.
You're going to use the Coulomb's energy to spin around, right? Where are your Coulombs? Down low. Okay? When I say pass, you pass. Got it? Everybody's got to do their job. Are you ready? Pass. 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 Now, pass. Now, you're going to notice something. It works fairly good. Nobody's dropped anything. I'm just kind of irritated. Can we pass as fast as we did before? We can't quite pass as fast as we did before because we've got this light bulb that's a little spinny, right? Okay. And also, you'll notice that if I compare temperature, who's the hotter? The light bulb, right? You're doing all the work. You're getting hotter. So we've already decided something here, though. The wires don't seem to get hot, and the light bulb does. Hot dang, you know? Like, this is working. Let's complete the circuit a little bit, or continue using this circuit. Niels is going to be, he's going to be the boss. He is going to decide what happens in the whole circuit. We're going to call him a switch. Okay, Niels, yes. You're the switch. And if you want to pass, you just stay where you are in the complete loop, and you can just pass, right? However, if you decide, or I say, open, you would want to stand, sort of rotate out of the circle so that you would have no one to pass to, right? Now, if you can't pass to anyone, can you pass? You can't pass, right? You can't pass. If he decides to open, then nobody can pass. Now, where could we put the switch in this loop to prevent anyone from passing? Anywhere. Doesn't that make sense? Can't you see it? Students should be able to see it. Okay, our model then predicts that we can place the switch anywhere in this loop and it's going to cut the current. What we're going to do now is model the meters, because you can't see electricity, and when we get to the real wiring, the practical aspect of this, we're going to use meters. And the numbers that come up on those meters have to mean something. They're not just numbers. So we want to use the model to explain what the numbers mean and what the meters mean and how to hook up the meters. Now, Ann is going to be
a meter.
Our ammeter. Now, after a while, you sort of, you get in, you slur it a little bit, and it becomes an ammeter. And Am, your job is to count. Can you count?
I think so.
Okay, right. Every time a block goes, you pass a block, I want you to count. Because you're going to model counting the coulombs, and I'm going to model the time. Remember, the advantage of models is you can slow things down. So I'm going to decide how long a second is. I feel pretty important here, I get to tell you when to pass, and I also get to tell you how long a second is. That's kind of cool. Good, I got some sort of godlike personality here. Okay, you ready? You want to pass again? Because you're getting a little bored? Okay, so okay, let's go. Here we go. Switch is closed, good, yeah. Pass.
What?
Shh, just, yeah, it's all right. Pass. Pass. Oh, that's good. Pass. Pass. Am, how many coulombs was that?
6.
Now, let's also think about where we could put the ammeter in the circuit. Would it matter if I put the ammeter there, or there, or there? It wouldn't matter, right? She passes 6 coulombs, you pass 6 coulombs, and you pass 6 coulombs. Everybody passes 6 coulombs. One of the things I forgot to mention that I should have before is another thing this models is that as soon as the switch is closed and the coulombs start being passed, how long does it take for that coulomb over there to be passed? It's almost instantaneously, isn't it? If a coulomb moves here, a coulomb moves there. How fast are the effects in real wires? Almost instantaneously. We need another volunteer. Oh, Doug, you pick him this time.
Well, actually, she's out of line, so.
Good point. She's out of line. Thank you for
come
volunteering.
Here, we can give the voltmeter. You have meter sticks in your classroom, so you can use the voltmeter to measure differences in energy.
If you come over to the battery and you want to measure the amount of energy the battery gives a coulomb, you've got to measure actually 2 things. You've got to measure the level it starts at, and you've got to measure the level the energy ends at, don't you? So how do you hook up a voltmeter? It has to be hooked up around things. She has to measure the difference from one place to another place. Voltmeters are always hooked up outside of the circuit around things. Get the idea? Now let's just say that this is 1 volt of energy, right? Excuse me. 1 joule of energy for every coulomb, that's a volt. And that's the energy between the coulombs there, right? Where's your coulomb? Up there, your coulomb. Voltmeter, could you come with me, please? Because we've already measured 1 volt there. And we're going to come around here, right? These are all high coulombs, high coulombs, high coulombs, high coulombs, high coulombs. Oh, now we get to the light bulb. Now, measure the difference in energy in the light bulb. How much energy is being used by the light bulb from here to here? What's the energy compared to back there?
About a volt.
About a volt. In fact, it's not about a volt, it is exactly a volt. The energy gained at the battery is equal to the energy lost at the light bulb. And the voltmeter is outside the circuit. The ammeter is in the circuit. The coulombs have to go right through the ammeter. But the voltmeter measures the energy differences of, like, outside the circuit, okay?